Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be taking a look at how to compute the probability of single and compound events. Don't forget, we have tons of support resources at our website, Mathgotserved.com, or simply take a look at the links in the description below. Alright, to get us started, we're going to take a look at some formulas that will be guiding our problem solving process, okay? So we're going to start by looking at the formula for single events, probability of a single event. So the probability of a single event is expressed as P of event is simply the number of desired outcomes. The number of desired outcomes divided by the number of possible outcomes. Okay? Divided by the number of possible outcomes. Alright, now if you have compound events, you could have one that's dependent or independent. So let's go ahead and distinguish between both of them. Okay, so let's say you have two dependent events. Alright, so what's the probability of getting a situation where you have a probability of A and B, event A and B, where the events are dependent? Probability of getting A and B is simply the probability of A times the probability of B given A. Okay, so think about dependent events as events that are connected to each other. All right, basically one event affects the outcome of the other. There is some kind of change in the sample space after the first event. Okay, that's why we have probability of B given A, because the probability of B is affected by the probability of A. Okay, all right, so this is a formula when you have dependent events. And then on the flip side, you have independent events where one does not affect the other. All right, so in that particular case, the probability of A and B for independent events is probability of A times the probability of B. Okay, for independent events, they are not connected. So for example, you're flipping a coin repeatedly, right? The first flip does not change the geometry of the coin. All right, so you have equal likelihood to get a head or a tail, 50% each, regardless of how many times you flip the coin. All right, so if there's no change to the sample space for two events in sequence, then you have a situation where the events are independent. All right, so simply probability of A times the probability of B, because the probability of B given A is the same thing as the probability of B, because the probability of B is not affected by A. All right, so that's how you have this formula right here. Okay, now let's go ahead and take a look at some examples. But before we do that, let's take a look at some examples, maybe just one example of each case. Okay, so number 3, we want to look at an example of a dependent and independent event, probability event. So let's start with a dependent example. An example of a dependent event is when you, let's say you pull cards out of a deck without replacement. All right, pull 2 cards out of a deck without replacement. So why is this dependent? Remember, dependent causes a change in the sample space of the subsequent event, right? So when you pull a card out of the deck and you do not replace it, you have one less card on the deck. So when you're pulling the second card, you're pulling a card out of a deck of 51 cards. All right, so don't forget, dependent events involve change. So when you have no replacement, you're changing the sample space of a second event, hence it's affected, resulting in a dependent situation. All right, how about independent? An example of an independent event. This one involves no changes in sample space. So for example, if you flip a coin and toss a fair die. These two events are independent because the coin has nothing to do with the die. It doesn't change the possible outcomes of getting the die, a particular number on the die in any shape, form, or fashion. Okay, so these are just examples of dependent and independent events. All right, let's consider the following examples. So suppose you have a bag with 5 green, 3 blue, and 2 red marbles. All right, so you have to find the probability of the following outcomes if the selections are made randomly. All right, let's start with the first one. What's the probability of selecting a green marble? So solutions here. So number 1, probability of selecting 1 green marble is just a single event, okay? In this particular case, it's the number of green marbles divided by the total number of marbles. All right, number of marbles total. All right, so how many green marbles are there? There are 5 green marbles. And then how many marbles in all? You have 5 plus 3 plus 2, which is 10. So you have 10 marbles in all. So we have 5 over 10. We can reduce this. Just divide by the GCF, which is 5. Divide both sides by 5. And then you have 1 over 2. All right. So this is the answer in fraction form. So probability can be expressed as a fraction, a decimal, and a percent. So you can write it as 1 over 2 or 0.5 in decimal form or 50% in percent format. All right, so there goes your respective probabilities in 3 different formats. All right, let's take a look at the second question. What's the probability of picking a marble that is not red? All right, so for number 2, probability of picking a marble that's not red just involves finding, this is a single event probability again, find the number of non-red marbles divided by the number of marbles total, okay? Or total number of marbles. All right, so how many marbles are not red? There are 10 marbles in all, okay? 2 are red, so that means that 8 are not red. So non-red marbles are the green and blue marbles, so that's going to be 8 divided by total number of marbles, that's still 10. All right, so let's simplify this. Just divide by the greatest common factor here, which is 2, so divide by 2 top and bottom. And then you get 4 over 5 in fraction form. And then if you can express this in decimal form, which is 0.8, just simply long divide. Or you can express it in percent, 80%. Just move the decimal points 2 places to the right or multiply the decimal result by 100 to convert it from decimal to percent format. Alrighty. Okay. Now let's move on to the third one. What's the probability of picking a gray marble? So the probability of picking a gray marble is as follows. Probability of picking 1 gray marble is equal to the number of gray marbles in the bag divided by the total number of marbles in the bag. Alrighty, so in this situation, how many gray marbles are there in the bag? In the bag, there are a total of 0 gray marbles. Okay, there are no gray marbles in the bag. So let's write that down. So there are 0 gray marbles in the bag and a total of 10 marbles in all. Remember, we only have green, blue, and red marbles. There are no gray marbles in the bag. So if we simplify this, 0 divided by 10, you have 0 or 0% possibility. So this is an impossible outcome. Remember, probability goes from 0 all the way to 1, or 0% to 100%. 0 means it's impossible, and 1 or 100% means it's a guarantee, and everything in between, okay? All right, so the next one is a compound event. We have multiple selections going on here. Number 4, what's the probability of getting a blue and then a green without replacement of the first? So for number 4, this particular one, since there is no replacement, is going to be a dependent situation. All right, because it being dependent or not helps us to determine the right formula. So we're going to be using the formula for dependent. Remember, when there's no replacement, there is a change in the sample space when you're making the second selection. All right, the first selection impacts the second, so there's a change, or they're connected, so it's dependent. All right, so probability of picking a blue, let's just call it B, and a green without replacement, which makes it dependent, is going to be probability of selecting a blue times probability of selecting a green given that a blue is selected. All right, probability of selecting a blue is the number of blue marbles times, divided by the number of marbles in all. Okay, and then so let's write it down. So it's going to be number of blue marbles divided by total number of marbles. That's for the first one. And then probability of getting a green given a blue has already been pulled out is number of green marbles. It hasn't changed, okay? The assumption here is that a blue has already been pulled out. So, so the number of green marbles divided by, since one marble has already been pulled out without replacement, you're going to have to divide it by the total number minus 1. Why are we subtracting 1? Because in the first selection, a ball was pulled out and it was not replaced. Okay? So when you have dependent events, subsequent probabilities are different from the original one in the denominator position. Okay, so something to keep in mind. All right, so what does that give us? Number of blue marbles. How many blue marbles are there? 3 blue marbles. So 3 over 10 is the first one. Probability of getting a blue, and then times probability of picking a green given a blue. So green, there are 5 green marbles. 5. And then we're going to divide by what? Divide by 9, because there's one that has been taken out without replacement. Okay, we can reduce this. 3 goes here 1, 3 goes here 3, 5 goes here 1, 5 goes here 2. You get 1 over 6 in fraction form. You can write it as a decimal, which is approximately 0.16, or you can write it as 0.16, the 6 repeating, or in percentage format, 16.6 repeating percent. All right, so those are the 3 ways that you can express it. So 1 over 6, 0.1 with a 6 repeating, or 16.6 repeating percent. All right, let's take a look at the last example, number 5. What's the probability of picking a red marble and then a blue marble with replacement of the first? Okay, so for number 5, in this particular one, we have a replacement happening. So when I pull a marble out and you replace it, the second event is not affected by the first since the original marble was replaced. The first selection was replaced. So there is no change in the sample space of the subsequent event. So that means that the two events are independent. So we're going to be using the independent probability formula. All right, so probability of selecting a red and a blue is simply going to be the product of the individual probabilities, probability of a red times the probability of a blue. Okay, so this is going to be probability of red. How many marbles are red? I think it's 2, right? So 2 red marbles, 3 blue. So probability of a red is 2 out of 10. All right, times probability of blue. Now the probability of selecting a blue is not impacted by the first one because the original whatever you selected was returned. Okay, so we have just like a new problem situation. So there are 3 blues times the probability of blue, which is 3 out of 10. If you compare this with number 4, you notice that in number 4, the denominators were changing, was reducing by 1. That's what happens with dependent events, right? Because changes are happening. But independent, you notice the denominators are both the same. They're both 10. The total number remains the same because there's no change in the sample space for both events. All right, so we can simplify this. 2 goes here, 1, 2 goes here, 5. And then you have 3 over 50. You can write it as 3 over 50 in fraction format. And then you can divide this by 3 divided by 50. You can use your calculator or long division. And that's going to give you 0.06. Or in percent format, multiply this by 100 and move the decimal place 2 places to the right. The decimal point 2 places to the right. And that will give you 6%. Okay? So there goes your 3 possible answers for question number 5.